In this video, we are going to introduce modular arithmetic. Now we'll get to the formal definition of modular arithmetic at the end of the slides. It comes very naturally from the things that we've been studying, but I think that some examples to introduce what we're doing are really helpful in understanding that you already know and do modular arithmetic on a regular basis. And I'd like to just point out some of those examples as motivation for studying this process more generally. The first example that comes to mind when talking about modular arithmetic, which we'll get to, is working on a clock. The best example I can think of is that in the United States, there are two different ways to talk about time. There's civilian time, and we use the numbers 1 through 12 with AM for the morning and PM for the afternoon. And then there's military time, which doesn't want to really deal with the AM and the PM, and therefore just uses the 24 hours that we have in a day, each one getting their own hour. And it's very straightforward to convert from military time to civilian time. If in military time it was 15 o'clock, we could simply subtract 12 from the 15. That would give us a number of 3, which is what we would then refer to as 3 p.m. Similarly, if we had something like 20 o'clock, we can subtract 12 from that value, and we would get the number 8. So 20 o'clock would be equivalent to 8 o'clock p.m. With numbers that already fell within our standard range, like 4, there wouldn't be any translation to do at all. But we could be a little bit more general with this process if we wanted to be. So a standard single day has just those 24 hours. But if we wanted to be more general, we could say something like, well, what would 49 o'clock mean if that were a thing? Now, if we subtract 12 from 49, we're going to get 37, which isn't a number that appears in either civilian or military time. So subtracting a single copy of 12, as we did above, doesn't get us into the range of anything that makes sense. But if we subtract 4 copies of 12, we would arrive at the number 1. And so 49 o'clock would be equivalent to 1 o'clock. And if we wanted to do this process as generally as possible, we could have any kind of a clock. It could be A o'clock for whatever value of A we want to consider. And the process would be the same. We subtract off some number of copies of 12 until we arrive in this range between 0 and 12, exclusive on the 12, inclusive on the 0. And once we arrive at that number that's in that range, that's a number that would make sense for civilian time, and we can do this translation process. Another motivation that we're really comfortable with is doing modular arithmetic on a calendar, but something has changed a little bit here. You'll occasionally hear modular arithmetic described as doing math in a circle. It's very clear where the circle comes from on the clock. It's a little bit more of a figurative circle when you're working on a calendar. But there should be a lot of similarities between this example and the last example. Say we're starting at a particular day and we're counting down the number of days till some other sort of day that's meaningful to us. And we determine that there are 24 days in between the day we're currently at and the day we're looking forward to. One thing we might be thinking about on this first day is, okay, 24 days from now is this big event that I'm looking forward to. What day of the week does that event fall on? In the previous example with military and civilian time, the number 12 was very important to us. Every 12 hours, the process of counting started over. In the calendar example, every 7 days, we'll have cycled through all of the days of the week and done this figurative circle, and we will be on the same day as the day in which we started. So in that sense, completing a cycle of 7 days is a negligible thing, and we can take this value of 24 and we can subtract off some multiple of 7 days, in this case 3 multiples of 7 days, and that process, in taking away those 21 days from the 24 days, that's really negligible. And the number of days left over at that point would be 3 days. So what this process gives us the power to do is say, if it's currently December 1st and 24 days from now, I want to know what day of the week it will be, instead of counting out the 24 days and seeing where I land on the calendar, instead, I can just count forward 3 days. And the day of the week, 3 days from now, is precisely the same as the day of the week, 24 days from now. And we can arrive at our answer in a much simpler way. Calendars and clocks and time give us a lot of really standard examples of where we use modular arithmetic in life, but there are actually a lot of places where we use modular arithmetic in life where we identify some sort of cycle that's important to us, and after that cycle, the pattern just repeats over and over and over again. And so we replace large numbers with the smaller value that they're the same as earlier on in the cycle. So one example of that, if you're musically inclined, is when you look at a key signature in music. The key signature, 4-4, is sitting right over here, that 4 sitting on top of the 4. That tells us that there are 4 beats in a measure, and the quarter note is getting the beat. So each one of these things with a vertical line here and a vertical line right here, this distance is called a measure. And if you know how to count music, you know how to attribute the beats to the different notes within that measure. So what I have written down here along the bottom are the beats starting at beat 0, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 beats. We can attribute the number of beats as we progress in the sequence of music. But if you were a musician playing this music, in your head, you'd be performing a 4 count and then restarting that 4 count over and over again. So you wouldn't count 1, 2, 3, 4, 5, 6, 7, 8. You would count 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 over and over. If you want to see that process of visualizing the beats and attributing the beats and how a musician would count those beats, I've got a little audio clip for you. So I'm going to have the music be playing, and I'm going to be recording how a musician would count if they were keeping track of the beat in this music. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And so on. Now another thing I'd like to point out to you here is that if you remember that a measure is the distance between these vertical lines, we've got 1, 2, 3, 4, 5 measures here that are of importance for the tune in the song that we just heard. And I think of that as sort of like a stanza to poetry, and we listen to that pattern once, and if we were to continue playing the song, we would repeat to the beginning and play those 5 measures all over again. If you take a look at our music and the way it's written right here, there are 5 measures in each line of the music right here. And that's so that if we get distracted, if we were maybe playing in an orchestra or a band, as opposed to just playing a work independently, if there were a long period where our instrument was not playing and we needed to eventually pick up, we may not keep track of the total number of measures we are into the song, but we may keep track of how many patterns of the stanza we've heard before it's our turn to come back in and play again with our instrument. So another modular arithmetic operation you may have going on in here with the music is you may be counting measures instead of counting beats within the measure and recounting after every 5, since every 5 corresponds to a line on your sheet of music. And modular arithmetic, we've seen its place on calendars, on clocks, in music, We also use concepts of modular arithmetic when we're working on what are called error correcting codes. And ISBN numbers are one place in particular where modular arithmetic is used to encode information about the book. That's why if you're buying textbooks for class, it's very important that you have the exact ISBN number of the book you'll be using in that class. Having a different ISBN number is encoding fundamentally different information about the book, and this thing called a check digit scheme is making sure that there haven't been any errors in transcribing that ISBN number for safety when we're transmitting this sort of information all over the internet. So not a lot of detail to come right here, but ISBN numbers are another place that modular arithmetic comes up. And modular arithmetic is in fact so ingrained in our brains that we have been using modular arithmetic ever since we started talking about odd and even numbers. Or in other words, when we classify numbers by their parity, we're actually using something that's called modular arithmetic. So I'd like now to get into formally what it means to perform modular arithmetic. And this all comes back to the Quotient-Remainder Theorem, which we've covered in previous videos, but I've restated right here for your convenience. And I've actually changed what was previously a and b to a and n, because when you're working with modular arithmetic, it's a lot more common to call this integer called the modulus, n. But here's the idea. Let's find a special number, a number that's important to us that's indicating some type of figurative circle, like 12 with the clock, or 7 with the days of the week, or in our music examples, 4 for beats per measure, and 5 for number of stanzas in the sheet music. All of those are different examples of values we could put in for this number n. The process that we were doing in each of those examples, when we took some arbitrary number and subtracted from it a multiple of the special number, that's this Qn part right here, and we then replaced the arbitrary number with this remainder that fell strictly in between 0 and the special number, inclusion on the left, exclusion on the right. All of that process was coming from the Quotient-Remainder Theorem, and the process of associating the arbitrary number with its remainder, modulo n, is called performing modular arithmetic. In this situation, that special number that's defining the figurative circle is called the modulus. So n from this equation is called the modulus. And the way that we would write this on paper as mathematicians is we would say A, 3 lines are mod n. That's the way we would write it. The way we would say it out loud is either A is congruent to R mod n, or you might hear it said A is equivalent to R mod n. So finally, just returning to those examples that we started out the video with, we would write things like 49 is equivalent to 1 modulo n, and we would write 24 is congruent to 3 mod 7. That's the process of modular arithmetic. It's derived from the Quotient-Remainder Theorem, and it really is a natural thing that we use all the time in everyday life.